Hello everyone and welcome back to the next lecture of control systems. In this presentation we are going to discuss initial and final value theorems. So let's get started. Before moving on to initial and final value theorems, we will discuss that what is an initial value and the final value of a function. So the initial value is the value of a function at t equal to 0 plus, and the final value is the value of a function at t equal to infinite. The final value of a function is also called as the steady state value. For example, if we have a function f of t equal to e to the power minus 2t ut, the initial value of this function is at t equal to 0 plus. So if we want to calculate the initial value, then it will be f of 0, which is the function value at t equal to 0. So we will substitute t equal to 0 in this function and we will get e to the power minus 2 multiplied with 0 u of 0. E to the power minus 0 is 1, so we will have the initial value equal to 1. Similarly, if we want to find out the final value of this function, then we have to substitute f of infinity, which is the function value at t equal to infinity. It will be equal to e to the power minus 2 multiplied with infinity u of infinity. E to the power minus 2 multiplied with infinity is e to the power minus infinity, and its value is equal to 0. So these are the initial and final values for this function, and if we want to plot this function, then we will have this curve. We can see the initial value, that is the value at t equal to 0, is equal to 1, and the final value is approaching to 0 at t tending to infinity. So this is an exponentially decaying curve, and we can see that it is very easy to find out the initial and final values of a function which is in time domain. But suppose if the function is in frequency domain, like f of s equal to 1 over s plus 2, and if we want to find out its initial and final values, then we need to take its inverse Laplace transform to convert this function to its equivalent time domain, and then after that we will take the values at t equal to 0 plus and t equal to infinity to find out its initial and final values. But instead of taking the inverse Laplace transform of this function, we will use the initial and final value theorems. Initial and final value theorems are the properties of Laplace transform by which we can find out the initial and the final values of a function in the S domain. So now we are done with the initial and final value of a function and the significance of initial and final value theorems. We will now discuss the initial value theorem. The initial value theorem is the property of Laplace transform by which we can find out the initial value of a function in the S domain. Suppose f of t is a time domain function having a Laplace transform f of s, then the initial value of this function will be limit t tending to 0 f of t, which is equal to f of 0 plus, and it is equal to limit s tending to infinity s multiplied with f of s. So the initial value of this function in the time domain is limit t tending to 0 f of t, and its initial value in the s domain is s tending to infinity s multiplied with f of s. Time and frequency are reciprocal of each other. That's why in the time domain when t tending to 0, in the s domain s is tending to infinity. So both the two are the initial value of the same function. One is in the time domain and the other one is in the frequency domain. So this is the initial value theorem, and now we will understand this theorem with the help of an example. Suppose f of s equal to 1 over s plus 2. Find the value of this function at t equal to 0 plus. This is the same function that we have discussed in the earlier section. Now we will find out its initial value by the use of initial value theorem. So moving on to the solution, its initial value in the s domain is limit s tending to infinity s multiplied with f of s. F of s equal to 1 over s plus 2, so we will have limit s tending to infinity s multiplied with 1 over s plus 2. Now s is tending to infinity, so we will take s common in the denominator and we will have limit s tending to infinity s over s multiplied with 1 plus 2 over s. We have taken s common in the denominator. Now s in the denominator and in the numerator will get cancelled. And if we take the limit s tending to infinity, then we will have 2 over infinity in this term and it will be equal to 0. So we will have the limit equal to 1. So the initial value of this function is equal to 1. and we have calculated this by the use of initial value theorem. So now we are done with the discussion on initial value theorem. We will now discuss the conditions. So for the initial value theorem to be applicable, signal ft must satisfy two conditions. Condition number 1 is it is applicable only when f of t is equal to 0 when t is less than 0. That is, from minus infinity to 0 minus, the value of the function f of t should be equal to 0. The condition number 2 is f of t must not contain any impulse or discontinuities at t equal to 0. So it should not contain any impulse or any discontinuity at t equal to 0. If these two conditions are satisfied, initial value theorem is applicable. And in this way, we are done with the discussion on initial value theorem. We will now move on to the final value theorem. The final value theorem is the property of Laplace transform by which we can find out the final value of a function in the S domain. Suppose f of t is having a Laplace transform f of s, then the final value of f of t is limit t tending to infinity f of t, which is equal to f of infinity and is equal to limit s tending to 0 s multiplied with f of s. So the final value of this function in the time domain is limit t tending to infinity f of t, and the final value in the s domain is limit s tending to 0 s multiplied with f of s. So in the time domain, when t is tending to infinity, in the s domain s is tending to 0. Both of them are representing the final value of the same function, but one is in the time domain and the other one is in the frequency domain. So this is the final value theorem, and we will understand this theorem with the help of an example. And the example is given as f of s equal to 1 over s plus 2. Find the value of this function at t equal to infinite. We are having the same example and we will now find out its final value by the use of final value theorem. So moving on to the solution, the final value of a function is limit t tending to infinity f of t in the time domain. So limit t tending to infinity f of t, which is the final value, and in the s domain it is equal to limit s tending to 0 s multiplied with f of s, and f of s is equal to 1 over s plus 2. So we will have limit s tending to 0 s multiplied with 1 over s plus 2. Now if we substitute the value of limit s tending to 0 here, we will get the value of limit equal to 0. So the final value of this function is equal to 0, and we have calculated this by the use of final value theorem. So now we are done with the discussion on final value theorem. We will now move on to the conditions of final value theorem. So for the final value theorem to be applicable, signal fs must satisfy two conditions. Condition number 1 is all the poles of fs must lie in the left half plane. When we draw the pole 0 diagram in an S-plane, then the part of S-plane which is in the right half of origin is the right half plane, and the part of S-plane which is in the left half of origin is the left half plane. So for the final value theorem to be applicable, all the poles of Fs must lie in the left half plane. Now condition number 2 is f of s must not have more than one pole at the origin. Fs must not have more than one pole at the origin. So these are the two conditions which must be satisfied for the final value theorem to be applicable. Now we will take some examples to understand that if these two conditions are not satisfied, then why the final value theorem is not applicable. Given f of s equal to 1 over s minus 2, find the steady state value. So we are given a function f of s equal to 1 over s minus 2, and we need to find out the steady state value or the final value of this function. So if we move on to the solution, we can see pole of fs is at s equal to 2, which is in the right half plane. So this function fs is having a pole which is in the right half plane. So we can say final value theorem is not applicable. Now why it is not applicable? Let's check this by taking the inverse Laplace transform of this function. We will have f of t equal to e power 2t multiplied with ut. Inverse Laplace transform of 1 over s minus a is e to the power at ut. That's why we are having f of t equal to e power 2t ut. This is an exponentially increasing function, and if we plot this curve, then it will be an exponentially increasing function. The final value is not defined, and that's why the final value theorem is not applicable. Similarly, if we take one more example, if f of s equal to omega over s square plus omega square, then the value limit t tending to infinity f of t is. In this case, we are given this function f of s equal to omega over s square plus omega square, and we need to find out its final value. If we move on to the solution, we can see the poles of this function are at s equal to plus or minus j omega. If we plot these poles in the pole 0 diagram, then we can see it has a pair of complex conjugate poles present at the j omega axis. And in this case, the final value theorem is not applicable because the final value is not defined for the function. Let's check by taking the inverse Laplace transform. So f of t, which is the time domain function, is equal to sine omega t, which is the inverse Laplace transform of this function. And we can see it is a sinusoidal curve which oscillates between two values, which is -1 and +1. The value of sine function lies between -1 and +1, but the final value is never defined. So we can say that this function is an oscillatory function whose value oscillates between -1 and +1. So now we know the conditions of final value theorem and the reason that why we cannot apply the final value theorem in these two cases. Whenever the function is having pole in the right half plane, we can say the function is an unbounded function and the final value is not defined. Similarly, if the function is having pair of complex conjugate poles in the j omega axis, then we can say the system is an oscillatory function and again the final value is not defined. In both the cases, we cannot apply the final value theorem. And in this way, we are done with this lecture. Thank you for watching this lecture. I'll end this lecture here. See you in the next one.